We all take some degree of risk in life and business, but we should eliminate that risk when it comes to your equipment calibration. Bad measurements lead to catastrophic consequences. These bad measurements could be used on medical equipment, airplanes, cars, seatbelts, or buildings, so your exposure and liability could be horrendous. When it comes to your force or torque equipment, you need to minimize your risk, and we'll show you how. Let's first define measurement traceability. That measurement traces back to the International System of Units, SI. For force and torque, these SI units are time, length, and mass. The pyramid starts with SI at the top, then National Measurement Institute, NMI, like NIST. If NIST did the calibration of the force weights, then the next tier would be a primary reference laboratory, like Morehouse. Morehouse performs calibrations on load cells for the lower tiers, accredited calibration suppliers, followed by working standards who in turn calibrate field equipment. Measurement uncertainty also keeps us honest. If we think about making a conformity assessment of pass or fail, the larger your measurement uncertainty, the more likely you are to fail an instrument. Using the analogy of a parking space, when your uncertainty is small, you have a large parking space to easily park your car. This small uncertainty means we have more space or range to pass an instrument. However, when your uncertainty is large, you have the smallest parking space, sometimes with not enough room to park. You have less range and sometimes no range at all to pass an instrument. Lowering your measurement uncertainties mostly depends on the performance characteristics of your equipment, the use of proper adapters, and the uncertainties of your calibration provider. Morehouse manufactures precision force measuring equipment, proper adapters, and has measurement uncertainties 10 to 50 times lower than many, which allows for lower test uncertainty ratios to pass more calibrations, increasing your customers' confidence in you. To lower your measurement uncertainty and risk, call us today.
Thank you for joining our webinar today about measurement risk. I wanted to take a few minutes just to introduce Morehouse and what we do today. So we manufacture force calibration products such as universal calibrating machine, deadweight calibrating machine, and portable calibrating machine. We provide force measuring equipment, calibration using international standards. These standards allow us to lower uncertainties of our customers' equipment, which, by the way, will also help to lower your force uncertainty. We enable customers to make better measurements, which makes the world a safer place. So in our force calibration lab, we offer both force and torque calibrations at a very high level of accuracy. We are a primary standards laboratory and offer deadweight calibrations up to 120,000 pounds of force that's known to within 0.002% of applied force. And we also offer other force calibrations up to 2.25 million pounds or 10 meganewtons of force, which is known to 0.01% of applied force. In addition to force, we also have a torque standard. It's the most accurate and the second most accurate in the world, which was purchased from the National Physical Laboratory in England. For torque, we have uncertainties of better than 25 parts per million. So why do we do all of this? It really comes down to our purpose, which is to create a safer world by helping companies improve their force and torque measurements. So today we're presenting this webinar to help educate people on what matters most. And one of those things is measurement risk related to these force measurements. So you're going to see here a picture in a minute that kind of displays what might happen if we do not perform force measurements properly. And this session is to help you make the world a little bit safer by helping others understand how to make better force measurements.
Yep. All right.
So with that, I'm going to hand it off to Henry, our presenter. Henry Zumbrum is the president of Morehouse Instrument Company since 2013, and he's worked at Morehouse for more than 20 years. Henry has a passion for measurement accuracy and reducing risk associated with these measurements that impacts our safety. One thing I've learned from Henry is just about these far-reaching impacts of force measurements on like some of these pictures you're looking at now with bridges and planes and cars that we drive in. So now I'm going to pass it over to Henry for the presentation.
All right, thanks, Heather. Yeah, so those that came in, it seems like a good time. People come in, 3, 4, 5 minutes late. We have and been developing YouTube videos such as the people at the beginning saw. I uploaded that one because you really can't share well or you don't hear the sound. But we have videos on TUR. We have 3 videos right now, and we're going to have 4. The next one's going to be on accuracy and certainty, the importance of definitions, and some other things. In that video, you saw the parking space analogy and some other examples. And as Heather was reading this, we were going through, and there was a bridge collapse. Here's another bridge collapse. And then pretty recently, we had this. The structures in Miami, where these, I believe these hotels were built around the 1970s, like 78. And there was another hotel really similar to this one, but years of inspection. And you start questioning, why does it happen? You know, what happens if we do not perform force measurements properly? This isn't just limited to force, right? But that's what we do, as Heather said. We do force and torque. This is also any measurements, right? Anything that happens, like you wake up in the morning, your phone works. Why does your phone work? All the stuff that goes into the phone, the chips that you hear the shortages and everything else about, they're all tested. Everything's tested. Engineers still to this day in 2021 design things and don't take account the level of risk. Not all, some do not take account the level of risk in some of this, right? And they design their parts. I just talking to a buddy yesterday where he did the radar. It was not the radar. It was a heads-up display that they had a big problem with, and he said it's out of spec. I took all these measurements out of spec. Talked to the engineer. Engineer says that's impossible. I designed it so you never need to adjust it. Look, people are all different. Didn't ask. Some people are metrologists. Some people are technicians. Some people are just here to learn. That's great. But anything and everything can go out of specification. I don't know of anything that does not, unless it's your standard, right, that you're disseminating down. But anyway, this session specifically is to help you make the world a bit safer. Start thinking about these concepts. Start thinking about, like, hey, would you know if you had somebody, falsifying documentation? Do you have checks in place? And as Heather said, we were one slide. I should have had this slide ahead of the other one, but this is my information, my email. If you have any questions, please reach out. But outcomes for today, learn about measurement risk and the importance of understanding it. The definitions, so important that we all understand the definitions. And we're all doing things that work for us, right? Following the standards. If you're accredited, you have to follow the ILAC documents. And specifically, ILAC P14 talks about, and 5.4 talks about short-term contributors. So we're going to get to that. TUR, a lot of people calculate TUR, test uncertainty ratio, yet I find that many people don't do it right. They ignore things or they make up their own definitions. So that creates a big problem if we haven't standardized the process. And of course, we'll talk about measurement risk and why things matter. Here, NCSLI, a great organization. If you people are not members, I encourage people to become members, join. They have a lot of recommended practices, learning documents, and other things. The reason I say NCSLI associated with this bridge collapse is this happened when the NCSLI annual conference is July. Back then it was in July, was going on. And this is a bridge in I believe St. Paul, Minnesota. And the collapse, was too thin gusset plate that ripped along the rivets, and additional weight on the bridge at the time contributed to catastrophic failure. My question then is, why? Was this plate tested? Who signed off on it, right? Did an engineer say we can use that too thin gusset plate? Bridge lasted for years, right? Why all of a sudden? What were the conditions? What deteriorated something enough to make this collapse? or what ward. Everything has a fatigue life cycle. So here, this is the Swedish ship Vasa. I like this one because someone commissioned it. You can look it up on Google. It sank in 1628, less than a mile into its maiden voyage. Basically, they commissioned this great warship back in the 1600s, and then they determined the why, the root cause analysis, right? If you're not familiar, the why. But archaeologists found, when they were doing some things, they found 4 rulers used by the workers. 2 turned out to be based on Swedish feet with 12 inches, and the other 2 were Amsterdam feet with 11 inches. So useless information here for everybody, that if you use the Amsterdam feet versus the Swedish feet, right, you can say, hey, did you know that Amsterdam foot was 11 inches back in the 1600s? And no one really will care. But we do when we make measurements. If you hire 2 carpenters to come, build your house, do you want them using the same ruler? Or do you want one that's measuring with 11 inches as a foot and another one with 12? What's going to happen to your doorways? What's going to happen to your drawers? What's going to happen to everything? So it's not going to line up. Talking more about risk, here's another video. As I said, you won't have audio with it because of the platform, but this is a stealth bomber. You can see here it's taking off. Something's not going too well here. And about right now, the pilot's going to eject. You're going to see it right there. So pilot ejects, plane crashes. Why? Why does that happen? Right? You can see, but let's tell you what we heard. I don't know. I wasn't part of the investigation. This is what I heard. But there were 2 intertwined causes of the crash. Heavy rains before takeoff caused fuel to get into the data sensors, which were responsible for calculating speed and altitude, amongst other things. That's what you can find online, right? However, why? The mixture of water and fuel caused condensation to build up on the sensors, which were near the plane's surface. Here's the why. Ready? Nothing completely out of ordinary. When maintenance crew were calibrating them before the flight, they were unaware of this buildup, causing them to calibrate it wrong. Now, the inside story I heard, which worries me because I don't know if it's true or not, was that there was a workaround procedure that everybody knew about, except for the person that was calibrating it, that knew what to do, and the procedure wasn't complete. I don't know if that's true or not, but I do know it's another example and another thing. When we talk about risk, we talk about probability times impact, and if your procedures aren't right, you bring on a new tech, whose fault is it when something goes wrong, when they follow that procedure? This one, only $2 billion. Pocket change for most of us, or as I like to say, the worst Eddie Murphy movie ever. Debatable Pluto Nash, where they had that monetary unit. So, what we're going to discuss: traceability, test uncertainty ratio, and what this means, measurement risk, and then 3 steps to lower your measurement risk. Those that saw the video know that this is the metrological traceability chain. The video showed that. But when measuring force, the load cell should be calibrating using measurement standards traceable to the SI through a NMI, National Metrology Institute. They are recognized under the CIPM MRA, and that recognition is necessary as some NMIs cannot provide traceability. So if we go to NIST, NIST says metrological traceability requires the establishment of unbroken chain of calibrations to a specified reference standards, typically to national or international standards, in particular realizations of measurement units of the International System of Units. NIST assures traceability to SI. The important thing here is that this is a pyramid. All starts at the top. And as the top here being SI, as you disseminate down from these units, you have your NMI, NIST. Typically, NIST in this country, typically they are the best. We're chasing force over here, so NIST is 4 to 5 parts per million, depending on the day, temperature, humidity. Very tight. NIST, we sent most of our weights in our frames to be calibrated by NIST. They were calibrated with uncertainties of around 8 parts per million. That's for a standard uncertainty. Terms here being thrown around that everybody may not know what they mean. So a standard uncertainty is before any coverage factors or anything else is applied to it. So we've reduced everything to K equals 1. Did that for a reason. Most people will operate, hey, I want whatever's 95% confidence. That's a different term too. That's a little bit more out of what we'll talk about today. If you're interested in that, we have other documentation that we'll talk about calculating uncertainties. We wrote a guidance document for A2LA. We have a full guidance document on our website. If Heather's still listening in there, she can post the section of the website that people can go to, documents. Really a hidden, it's not hidden, but a lot of information over 20 some years is being dumped on our website for everybody to grab for free. Measurement uncertainty sheets, all kinds of different guidance for force or torque. Doesn't mean you can't use that for anything else. It's just we made it for our customers. But then, so the National Metrology Institute, from there, they calibrated our standards. We calibrate them as a primary lab for accredited suppliers, working standards. And as you can see, if we keep going, the uncertainties get larger each step. And the important part of this is you cannot, and people do this, believe it or not, you cannot have an uncertainty greater than the lab that did the calibration. So if you have a super ultra piece of equipment, just something really, really great, someone says it's good to 005. You send it to a lab that's at 001, your starting point now is got to be worse than 0.01. So we'll talk about that as this moves on. But this is the guidance document, G126. Force examples are in there. Like I said, that's posted to our website. Here's just one simple picture of the uncertainty spreadsheet. It'll do EN ratios, calculate resolution, do it R&Rs between texts, it'll do all kinds of things. When we look at force specifically, types of instruments, and I'm throwing some terminology around there, such as primary standards, this is a tiered system approach. So tier 1, we have primary standards. That's typical no matter what you do, your discipline. And that is like dead weight. And that's what we showed earlier, where we have dead weights. And then tier 2 would be secondary standards. That's like your load cells, your proving rings. Tier 3, that could be even more load cells, crane scales, dynamometers. And then tier 4 ultimately is the testing machine or materials test. You know, those documents that are in the news that were falsified would come under here. Someone most likely did a material test and someone just signed something maybe without getting it done. I don't know. More will shake up. There's the deadweight machine right here. This is our 120,000 pound deadweight machine, over 500 kilonewton machine. And then because dead weights are expensive, we're installing one right now in the Air Force Laboratory in Newark, 102 and a 30,000 pound. They take about 2 years to build, and they cost well over $1 million for a machine of this capability and capacity. Not many labs will go above it. NIST has a 1 million pound deadweight machine. I can only imagine. They built it in the 60s. I can only imagine what that would cost today. And just really rough numbers, like machine stainless steel, just a real rough would be $8 a pound, or $8 to $10 a pound. So based on that number alone, you can figure out ideally what a 1 million pound machine may cost. So Heather had said earlier, we have torque capability. We bought that from the National Lab. That was recognized with the CIPM. That's a picture of our machine here. Second most accurate machine in the world. But what are we doing? We calibrate those. We use our primary standards. People can go to NIST. I encourage people to go to NIST. NIST is very expensive and the turnaround time's a lot longer. Our turnaround time is typically 7 to 10 business days. We have expedite options, though they can go here or they can use primary standards. And you saw that our uncertainties are higher than NIST. So they can go use us. We calibrate then the secondary working standards that are used to calibrate other things. And back to that hotel, back to bridges collapsing. What could happen if you fail to get the measurements correct, right? You get incorrect concrete strength measurement, incorrect steel strength measurement, cables not checked properly for pre-stress or post-tension. What happens if we just say, I'm not going to do it? Or engineer calculated it out. It is so easy on these calculations to have a plus or a minus be mistaken. It is so easy to miss a decimal place. And when you do that and you fail to test, a lot of times bad things happen. So I'm going to ask a polling question here. This is going to be 1 minute, right? If I can open poll, I think. So 22 people online. I'm going to ask a question. I have a 10,000 pound device with an accuracy of 0.1% of full scale, plus or minus 10 pounds. My calibration certificate says the unit reads 10,000 pounds when 10,000 pounds was applied. Is my device in tolerance? Here's what I have. Perfect. Perfect measurements. Is it in tolerance? Got 3 yeses and 1 no. And 18 people not paying any attention. Now, I kid. I actively amuse myself because I'm the only one talking. But is it intolerance? Think about it. We got 15 seconds left. We got 8 yes, 1 no. Are we going to get that one extra person to give us so I can say 80% yes, 20% no, or 90%? We did not. So the majority of people said, yes, my device is in tolerance. Well, this is a trick question because I can tell you, I don't know. I have no idea if it's in tolerance or not. I did not see the PO. What is our conformity assessment? What is our decision rule? We are all, if we're accredited to ISO 17025, there's a section in there that talks about decision rules that we have to ask. We have to talk about them. But the true thing is, on this, when we look at it, is who did the calibration? Right? Who did it? What standards did they use? Did they use standards that were capable of performing the calibration? Looking at this graph here, this basically says if I change the question, right, and I say, hey, I sent this to a lab for calibration, and they reported 0 error, yet when I graphed it, because of their uncertainties and because of the contributors that go into the TUR, when I graph this and everything's reading perfect, I have 12.39% risk, meaning these areas of the curves over these lines are a risk. So I have a 12.39% probability of false accept. Is that high? Is that low? Is that acceptable? If someone gave you something and they gave you odds, let's use the health realm, because I think everybody's had, hopefully not, but people have health scares, and you go online and you say you need a surgery, and would you rather the surgery where they say 1 in 1,000 people, 0.1% die, or would you rather the one that they say, yeah, this surgery, 12.39% of the people that go in for this surgery die or have serious complications? What one would you want? How would you seek a better doctor? Maybe the doctors. You're comparing 2 doctors. One doctor, one surgeon has a success rate of 999, and the other doctor has the success rate of 80%, 800. Who are you going to pick? Same things with measurements. So that's that measurement risk error. And if measurement uncertainty is not being reported properly by your service provider, there's no way to know if the device is in tolerance and you do not have a traceable measurement. And then me being snarky, because I'm smarky, and we come back to the Swedish feet, Amsterdam feet. Someone could say, would anyone use a ruler to calibrate their gauge blocks? I can get perfect measurements all day long. We might open a gauge block calibration service. And then the snarky people should be saying, hey, are you going to use the Swedish foot or an Amsterdam foot ruler? But no, I mean, that's really, would you do it? Most people would say no way. If you don't know what a gauge block is, that may not make as much sense. But what's going on? And my example is a little bit outdated, but it was a really good example. People may remember the Samsung Note 7 was catching fire, right? And what it comes down to is all measurements have a percentage likelihood of calling something good when it was bad and something bad when it is good. In terminology, real world scenarios, we call this consumer's risk and producer's risk. And the consumer's risk refers to the possibility of a problem occurring in a product that goes out to market, right? Toyota had like recalls. I use them in torque examples, so that's why good company. They make good cars. In fact, I own one, but they had recalls. All car manufacturers have recalls, right? Something happens, they bring it back. If it's bad enough, if it could impact you, that's a consumer risk situation, right? And sometimes a product passes undetected through the manufacturer's control time. Whereas on the producer's risk side of things, that's us catching it. Oh, our engineer, pick on engineers, our engineer made this product. We tested it. It was not good, right? We refined, retested. It does not go to the consumer. Toyota tests this new brake pad design and does all their stuff and determines no way, 10% failure, 1% failure, whatever it is, no way this thing is going out to the marketplace, right? So that's what we have. But when we look at metrology, we're calling these PFAs and PFRs, probability of false accept, and a probability of false reject. That means, hey, as a calibration service provider, we're rejecting something that might actually be good. That falls on us, right? What do? We typically adjust it, send it back out to the customer, right? Probability of false accept means we said something was good that actually has a really high risk. And when that customer then uses it, then now they've built up a global consumer's risk, and every instrument they calibrate and every instrument that instrument calibrates is subject to additional error, and it might mean the difference between something catastrophic happen and something, not. So if we look at this, I like this graph, probability of correct accept, they use that, probability of false accept, so actually out of tolerance, people can see that's a good example. We get to measurement related terms. Yes, decision risk is also in ISO 17025. I like the ANSI Z540.3, and I like that because we're going to talk about it as far as TURs and the definition of TURs is concerned. But what we're saying here and what we're showing here is we're showing a situation where there's 31.74% risk. But the nominal value is 10,000 pounds, and our measured value is 10,000 pounds. It's just the uncertainty is so high. Why is that? Well, if we go into the definition of TUR, defined in two documents, ANSI Z540.3 and ILAC G8. It's also mentioned in JCGM 106, but not defined. So here we go. I like the ANSI Z540.3 definition. It's more complete. It's the ratio of the span of tolerance of the measurement quantity subject to the calibration to twice the 95% expanded uncertainty of the measurement process used for calibration. So the reason I like the NCSLI, this definition better, is because if the tolerance is not symmetrical, then the ANSI NCSLI is much clearer. The other one doesn't really tell you as much with tolerances that are not symmetrical. So I prefer their definition. But if we look at that ANSI ANSI NCSLI Z540.3 and we look at the handbook, this is the only place I really found this nice complete definition, right? And it says for the numerator here, the unit of test, what it is, whatnot. But then the denominator, right? Numerator span of the tolerance. Most people get that. Not many people in industry confuse it. But the denominator, we have seen so many people, high-level laboratories, people you would never guess, say things like, I've never seen this definition. You're wrong. So here's to those people, and some may be in the audience right now. Here it is. This is directly out of the handbook. And it says for the denominator, the 95% expanded uncertainty of the measurement process used for calibration following the calibration procedure is used to calculate TUR. And it says right here, what does it include? Item being calibrated, except for bias of the MTE. The calibration process error includes temporary and non-correctable influences incurred during the calibration, such as repeatability, resolution error in the measurement source, operator error, error and correction factors, and environmental influences. So we captured it. If we go to ILAC P14 section 5.4, people can look at this one. I don't have it in the slides, but it says about short-term contributors. Those short-term contributors in general are going to be how good was the standard used for calibration? What is that calibration and measurement capability? Hey, what's the resolution and what's the repeatability of the UT? That's the basics, right? And people may say, oh, well, you don't need to account for the resolution. Well, you might not need to put it in there. But the only way you don't need to put it in there is if your repeatability is dominant contributor. Because manufacturers will give you specs where the accuracy is the same as the resolution. And you could make repeatable measurements all day long because the resolution is so coarse. If that's the case, you have to consider that resolution. You have to consider it no matter what. It's just a matter. We'll step through an example here and several different examples. So this is a 10,000 pound load cell. Really not much changing here. Just two pieces of equipment, primary standard versus secondary standard. There's a whole slew of things with timing and everything else. Lot of error over here, right? That's probably not captured in that calibration and measurement capability of 0.05. But besides that, let's go with what people may claim. So I have a 10,000 pound device. One, I'm using dead weights, and the other, I'm using this transfer machine with a load cell calibrated by dead weights. So on one hand, I have a TUR of 22:1, and on another hand, I have a TUR of 1:1, and that's using this formula. So if I think about those two machines and I do this graphically, it's what it looks like, right? Car example that people saw earlier. Remember the car that could easily fit into the space right here versus not fitting in too well, right? You got 4.55% risk. And in this example, we used 10,000 pounds, and when 10,000 pounds was applied, what do you think happens if I don't have a perfect measurement, right? In this scenario, we'll just move the graph over, right? So I move it over. One, I can still make a conformity assessment, right? 22.72, total risk 0. I can still say that instrument came in our lab, it was good, right? I can say I use method 5, I can say I can use method 6, I can say all kinds of different things as far as my decision rule is concerned. On the other hand, people say it's still within the specification limit, though my risk is at 34.47%. Are you okay with that? You okay sending something to a lab that gives it back, says it's good, but you're actually taking on a risk of 34.47? Like I said, think about doctors. Would you go? What doctor would you go to? There's the parking space. Those that didn't see the video, here's actual pictures. One, you can pull into the think about it this way. One, you can pull into the parking space, open the door, get out, put a lawn chair in, do whatever. I got room. I can pull in there, almost blindfolded probably, and still hit the target, right? The other, not so much. So we have things such as, I use terms such as method 5 versus method 6. Now, the ANSI Z540.3 handbook has about 6 decision rules in it, 1 through 6. 5 and 6 are the easiest to implement. There's one method 2 is fairly easy to implement, and then others require you to have a lot of history of the devices. So they're more difficult to implement. And then ISO, the 17025, doesn't really give us the guidance other than agreed upon decision rules. So you can make up your own decision rule, really. But that's hard to do. Go ask a lab to do that. Someone's going to need to custom program something, and that's never cheap. So method 5, guard bands on measurement uncertainty. Simplest to calculate. We're just going to subtract the measurement uncertainty. Test limit would be based on worst case PFA. And the problem with these is you could have a high probability of false reject because they may be too aggressive. Again, that's on the Cal lab. If we reject something and adjust it, that's fine. That's on us. And then we have this. How do we lower our measurement risk? So have the calibration provider replicate how the device is being used. Have competent technicians. These are all things you learn, right? Have people that don't falsify data. That would be in the competent technicians. Use the right equipment. Lower the uncertainties through the calibration provider. And they vary quite a bit. I did this TUR table here, which you can look at it. You say, hey, if I want this tolerance, and I have this load cell, that 10,000 pound load cell, and I have all these tolerances, what could I do? And basically anything, I made red anything that was under 4 times that. Other things, we talk about these. Have the calibration provider replicate how the device is being used. Here's with force, very common error, right? It's pin size. So one pin engages properly, 50 millimeter. One pin is smaller. What happens? Well, when I engage a larger area, I get more strain on the device, and hence I get more output. So here's a situation where manufacturer says 0.1% is the specification here, and all we did was switch pins, one 50 millimeter and one about that's 1.97 inches, and the other pin about 1.75 inches. All we did was switch them. 860-pound difference and a 1.72% error. How about scales? Truck scales, weighing. Our bridges, they pass an infrastructure bill. They're going to be redoing some bridges and some other stuff. How about those bridges that are deteriorating? What happens when you have a really heavy truck that exceeds the weight, sit on that bridge or go over that bridge? You feel safe? So what about if we calibrate those scales if we don't get it right? Can we pass something that might be completely overweight for the structure it's about to go on? And this situation involves truck scales. It's PT 300 and 3 different size plates here, right? So one's a 10 by 10, one's an 8 by 8, and one's a 9-inch round. So we took data. 10 by 10, ooh, we're going to fail this. It's way out, right? 8 by 8, that's good. And 9-inch. So not much different between the 9-inch round pads, 20 pounds at 20,000. Whereas if you look at the other ones, this device is well under a 1% accuracy. So look at this, just the error. So if somebody grabs the wrong adapter and tries to calibrate this scale, there's a chance that they're going to call it out and then they're going to adjust it in. So think about these. Have you or any of your technicians ever overloaded a load cell? If you're doing this long enough, you're going to mess up. Customers are going to send you equipment, and eventually you're going to have one of those moments where something happens. It makes us better as technicians, so it's a learning moment. I remember one of the first times I messed something up. Unfortunately, it went very well for the customer because I repaired it. It was a proving ring that we make. I repaired it, and I got the call. I repaired it, recalibrated it, the numbers that they had, it took me a long time to do. Numbers that they had after I repaired and did the cal were far better than it was before. Customer called me and said, hey, I have a question for you. And I said, yep, sure. What is it? I felt horrible. They said, can you mess up and overload all of our stuff? To which I was like, damn, I don't want to do that. I don't ever want to do it again, but it happens. So have you or someone you know ever used the wrong equipment? That happens all the time. The more people I talk to in this world, the more that someone made something. Not only when you make something, it might not be safe for your techs. It's, come on. What's it going to do to the employees' morale when you're jerry-rigging something to try to get something out the door? Is that really the tone you want to set for the workforce? I mean, good people are hard enough to find. When you have good people, you start doing things like that. You think you'll keep them? So have you ever signed a certificate you were unsure about? Happens, right? Hey, sign this, right? Do you know of any bad measurement practice in your organization that are not being corrected, or do complaints fall on deaf ears? How about your calibrate? Have they ever admitted to making a mistake? If the problem was not corrected, did it just go away? If you're working with a company long enough, you should see a mistake somewhere. We make them. We own up to them. It happens. It's just something that happens. So, we're not perfect, but we can mitigate measurement risk by making better measurements and replicating proper use of instruments. We can implement programs. We can do statistical process control. We can do almost everything we possibly can, and we can make that risk low. Like the doctor, the 1 in 1,000. You might say I can live with that risk. Much better than the 1 in 100. Much better than the 1 in 10. Right? So where are you? Where are you on that list? Are you a company that's 1 in 10,000? And for every 10,000 measurements you make a bad one? Are you 1 in 300 some, the statistical outlier? You 1 in 100? You can, it's going to be there somewhere. Are you 1 in a million? 1 in 10 million. So rules to lessen your risk: know the right requirements. This first rule involves knowing what is needed to accomplish the task at hand. Choose the right equipment. Always choose measuring test equipment capable of achieving measured tolerance required. Have the right processes, right? So we start looking at this, and you look at know the right requirements, right? So first rule involves, what do we need to accomplish the task at hand? Some basics. The more accurate the system, the higher the cost will be. People call me and say, what do you recommend for force? I say, well, how much is your budget? And it's not a loaded question. It's not like, we want to get the maximum amount of money. It's like, what do you really want, right? Can we find a solution within that budget? If somebody tells me budget's unlimited, I'm going to say, buy a deadweight machine, right? That's I need a £1 million standard. Well, do you have 10 million bucks? You want to buy a deadweight machine? We'll talk. Or do you want a 10,000 pound and have a couple 100,000? It just depends, right? So there's equipment out there. There's a meter out there for these measurements that we have in our lab. That's $60,000. Do you really, on one side, do you really need that? We don't sell it. I'll recommend it to anybody that wants to spend $60,000, but it's not a meter we offer. I wish we made it because it's freaking awesome. But our meters are generally in the $500 to $3,000 range. And depending on budget, we try to match what's appropriate for that prospective person. So for tests, TUR 4:1 will meet the guidelines set forth in ANSI Z540.1. It's a withdrawn standard, but a lot of people still follow it. A lot of people still say I need 4:1, and I want total risk less than 4%. Typically anymore, you're going to see everybody's moved to 2, not everybody, but you're going to see a lot of people 2% PFA. That's a rule we're seeing more and more. However, this one should probably die, and we should look more at location of the measurement, the CPK, which is the calibration process index, process capability index. We should look more into those type of things and the actual errors and everything else. And I don't care about 4:1 anymore. All I care if I send a device out is I want to know that the risk that the person calibrating my device, that I have less than 2% risk. I want less than 2%, but 2% is what's typically acceptable for most. If the requirement is 0.1% of applied and the stability of the device is 0.2 over 1 year, the device would need to calibrate. People do this all the time. This is one that really bothers me, and it bothers me because of the fact that they get out of tolerance, we adjust it, get it back in tolerance, send it out, comes back a year later, out of tolerance again, rinse, repeat, rinse, repeat. Comes back again, and it's a rinse, repeat scenario. We did have a question. We can send the slides. I made a mental note. I want to correct. One had a number somewhere that it shouldn't have been, just the slide number. But yes, we can absolutely send out the slide deck if you email Heather. So what happens when rule number 1 is not followed? BP Texas Refinery, look at this. Look at this. Nice, everybody's working. No idea what's about to happen. And then it blows up. So there's a 335-page final report from the U.S. Chemical Safety Board. Conclusion: organizational and safety deficiencies at all levels of the BP Corporation caused the March 23, 2005 explosion at the BP Texas refinery, the worst industrial accident of the United States since 1990. The report calls on OSHA to increase inspection and enforcement at U.S. oil refineries and chemical plants, and to require these corporations to evaluate the safety impact of mergers, reorganizations, downsizing, and budget cuts. Now wait, why did this happen? Well, distillation tower and attached blow drum overfilled. 7,600 gallons of flammable liquid was released. Liquid was ignited by an idling diesel truck. So we needed to have this stuff happen, and we needed that truck to be there. Probably only a matter of time. But look at this. High-level alarm malfunction. Where are the safety checks? Level transmitter miscalibrated with an outdated 1975 data sheet. Look at that. Risk. Who'd they send it to? Who did the cal? And then level transmitter indicated liquid level was falling when it was actually rising. Let's examine this. People that know the 5 whys, root cause, why? Cost cutting, great. Production pressures, failure to invest, big time. All you need to do is go to one business meeting today, and the general theme is going to be automate anything that can be automated, right? That's everybody. Everybody's going in that direction. So, but failure to invest. I guess you're not automating everything that needs to be automated. Lack of preventative maintenance and safety training, right? Procedural workarounds to compensate. Remember earlier I had the slide of you. Procedural workarounds. So cost. What's that cost? Well, 15 deaths, 180 injured, and then over $2 billion in several lawsuits. So BP acquired this facility. This history is from Amoco in 1999, and it just went on and on. The combination of cost cutting, production, all of it. And the safety report goes back to like 2002. BP commissioned a bunch of audits, and it just didn't nothing. And studies that revealed serious safety problems at the refinery, including a lack of necessary preventative maintenance and training. These audits and studies were shared with BP executives in London and were provided to at least one member of the executive board. BP's response was too little too late. Some additional investments were made, but they did not address the core problems in Texas City. In 2004, BP executives challenged the refineries to cut yet another 25% from their budgets for the following year. Now, how many people, there's a great book, and it's called To Engineer is Human, and it's by Henry Petrosky. Now, how many people, what he says is he says something along these lines. He says, sustained success makes us kind of lazy in reference to, and I'm paraphrasing it completely, it makes us not invest. All things are well. We don't need to look into that. It's worked for 15 years. It's worked for 20 years. Why do we want to do anything about that? You just want to spend all our money. But look at that. They had success. They didn't have any accidents. It's coming. They have reports that say, "Hey, this is coming." Kind of like the condo collapse in Miami, right? And then it happens, right? 15 deaths, 180 injured, 2 billion. What would it have really cost for them to fix their problems? So, rule number 2, choose the right equipment. Always choose measuring and test equipment that can achieve the measurement tolerance required. You know, this is a problem with our industry, and it's a big one. And several manufacturers, they're not metrologists. They're just making a product. They don't understand this stuff. They don't understand TUR, do not include the resolution or repeatability, or reference standards used to perform the calibration in their accuracy claims. Like, hey, I can do that. I'll put this thing over here. Someone says this is good to this, should be good enough to calibrate this. Yep, it's good, and they give it to you. On most of these instruments, no reference standard in the world may lower risk if the instrument shows any bias. I'm going to show you an example. This happens. This is a scale. It's the scale is repeatable within 10 pounds and has a resolution of 10 pounds. No matter what reference standard is used, the total risk will always be higher than 10% unless actions are taken. And when I say this, we're going to break this formula down. If we look at it, the top's easy, right? The tolerance is 10. Okay, 0.1%. What is that? Multiply the capacity by 0.1. No, actually, multiply the capacity by 0.1. That gives me 10 pounds. I'm going to add it and on one side and subtract it on the other, and I divide that. So tolerance is easy. CMC, who cares? That's our calibration and measurement capability. We're going to care eventually, but we don't care in this one because this problem here is the resolution. The resolution matches the uncertainty. So resolution 10 pounds and repeatability is found by taking the standard deviation of several test points. The more test points you take, the more it costs you as the cal provider, the better you can get this for the customer. Traditionally, there's a rule of diminishing returns here. I did 4. 5's a better number. 10's an even better number. 30's a fantastic number, but are you going to take 30 test points? Probably not. So, tolerance of the UUT, CMC, URES, and let's look at this. So, TURs, CMC, I just varied it. CNC is perfect. I sent it to the best lab in the world with 0 errors, right? That lab doesn't exist, but just for the sake of this argument, my TUR was less than 1-to-1 in all these, and it gets worse from there because the dominant contributors here are resolution and repeatability. How do you fix such a thing? Well, you can raise the tolerance. How many people bought something that said, I need a 0.1, I need to weigh an aircraft, specification is such, I need this, oh, this manufacturer has something that's 0.1% of applied, bingo, I need that. But if I want to raise this tolerance and seek a 4-to-1, something like a 4-to-1, I need to be at 0.52. I need to raise it 520%. That's pretty high. Improve repeatability only? Okay, so we say resolution still coarse, though I made that resolution coarse and I get a better, more repeatable measurement. So I take that to 0. Okay, take it to 0. Now I get a TURs. You can see the variable CMCs. Most people are down here, like at 0.025, 0.05. So I can get a TUR better than 1-to-1. It's still not 4-to-1 if that's the requirement. Air Force, this is one that I pick on Air Force a little bit because their requirement is 4-to-1. That's why I'm on the 4-to-1. You may not have that requirement, but improve resolution and repeatability. We did this. There's a paper online in those documents and tools. We had an instrument come in, this specifically scale, sent it to a company in Florida called Jaws Jackson Aircraft Weighing. They retooled the equipment. They put a new display on it. They did a lot of other things to it, and they made it better. And after they made it better, now we can back calculate, right? We can say, how good does that reference need to be to give us a 4-to-1? And what we came up with a 2-pound resolution and a CMC of 0.2, a 4-to-1. Again, that's not everybody's requirement. You don't always need 4-to-1, but if you want 4-to-1, this is a situation. That's how you're going to have to get it. You're going to have to severely modify the equipment. How do you fix it? You need to figure out a way to lower the uncertainty and adjust acceptance limit to limit lower and upper risk to less than 2%. Now, this is just, like I said, pretty much standard on a PFA. You might not be able to accept the 2% risk. So if that's the case, you just need to have that discussion with your cal provider. So right here, take more measurements, repeatability. This just shows here standard uncertainties. And again, TURs and risk. So if we don't go with 4-to-1 and we start going risk, this is basically saying we need to send this to a lab with dead weights, 005. Secondary standards do not achieve 005. We need to send this to a lab with dead weights to at least have a shot at getting this intolerance. And they're going to need to take a lot more repeated measurements down here than just the 3 or 4, which is going to cost us, the consumer, a heck of a lot more money, because I don't know of any lab that's just like, our standard practice is we take 3 measurements, but for you, we'll do 10, no upcharge, right? It takes time, and time is money. So that assumes what we talked about. That assumes that location is perfect. If it's out, it's going to get a fail, and it's going to be adjusted. That's assuming at 10,000 pounds, reads 10,000. Back to the question on slide 22, is it intolerance? So choosing the right equipment. The only way to lower total risk by a scale with better repeatability and resolution. Changing the process may cause all kinds of measurement problems, resulting in much higher risk. So here you have a thing. Maybe you're using a cal provider with dead weights and you like the price of someone with load cells. Someone goes, hey, I got this great price on calibration. I think we should send all our equipment there. It may make sense to do that. I don't know, but you need to evaluate it using that formula that I showed and say, will it make sense? What happens? Are they gonna fail more instrumentation? Are they following the right, guidelines? Are they taking, the uncertainty into account, or they're just reporting it? There's so many labs out there that just say, hey, I take the uncertainty into account by not considering it. Simple acceptance happens all the time. I just want simple acceptance. That pushes the risk back to you. Just understand it. It's if we're all on the same page, we're okay. If we're not, you're going to absorb the risk. And when I see labs absorbing the risk, a lot of them don't know they're absorbing the risk. Think about a person, a mechanic, making a measurement, right? If they use a caliper and said, oh yeah, this will fit. Is that okay? Might be, might not be. How about if it's a drawing for a critical aerospace part where there's a specifications and they don't take any uncertainty into account and say, hey, this device, someone passed it. Engineer says I need to, I need to measure within 100 thousandths. Yeah, looks good. How good's their caliper? Is it probably not good enough for that? They probably need to switch to a micrometer, but that's besides the point. So here's another example. Crane scales. Looking at the specifications. So this one, some specifications are 0.1 of applied plus or minus 1 count. What does that look like if we apply 501.5 pounds? Under that specification, we have a TUR of 2.5, 8-to-1, and we could pass the instrument. Not a problem, right? However, if the specification does not include that plus or minus 1 count, right? Specification, if this bottom one, what we're showing here is that same thing, except for we don't give the plus or minus 0.1 right? Same. Actually, I'm sorry, messed that up. I had another slide, and that's on me. So I apologize to everybody. This one, we're absolutely just moving the measured value from 500 to 501. And the location of the measurement here is key. Some of them have just one where you could run this through where you have the plus or minus the one count and it gives you more room versus not. This one, we just shifted the location of the measurement. So we basically, for this, we just need to be perfect. If it reads anything other than 500, we're probably going to have a problem. Here it reads counts by 1 pound, right? So we're either going to read 500 or 501. At 501, our risk is 4.23%. So really great equipment. Surprisingly, the specifications are really tight on these, but about 80% of them that come into our lab are in tolerance. So it's the purpose of this slide was just location of the measurement is key, but as I messed up on it, also understanding what they're saying. Is the specification plus or minus 1 count, or is it just one count? So different things for choosing the right equipment and what it can do. It can raise or lower. It can do different reference standards, can make things. So that's where we're going. Right equipment is going to be plumb, level, square, and rigid. Right. This is for force and going to have low torsion. The right equipment's going to replicate field use. Does this replicate your field use over here? Maybe. It probably does not. Right equipment, as this comes from ISO 376 over here for force, the right equipment's right adapters, right? I buy this expensive equipment and I use the wrong adapters, I'm going to get crap measurements. You saw that with the tension link there. So there's one, recommended adapters, top and bottom plates. Those that might be new to this can go back, look at YouTube video, look at everything, force measurement errors, look at the documents. We have a paper on adapters for force measurement for anybody that's interested. Really highly recommend. So third rule, have the right processes. Having training program and proof of training to validate individuals performing calibration or using the equipment. It's important to maintain and follow procedures that adequately support the end product performance. There should be a process in place that ensures all aspects of standards are being carefully satisfied in the calibration process and the use of proper adapters and making sure the instrument matches how it's being used in the field or lab. So we're wrapping up here. Went over. I do that. I'm very passionate about this topic. And here we have one, right processes. Right? Here's a manufacturer saying, our customers love the precision they get from these tension links. And they're showing this right here. They're saying, hey, before there wasn't a way to know how much torque was being applied, but now we can ensure we are meeting the required specifications. So anyone think this is a good way to measure torque? There's a lot of safety concerns here, right? But if we look at it, simple calculation, simple math on this. Right? This is where marketing doesn't understand metrology, and maybe other people don't understand metrology too. But if you just look at what torque is, right, and you look at this angle, if that's 45 degrees, some might argue it's not 45, but that's minutia. But look at apply the formula, apply it at 40 degrees. That picture right there, I estimate, is showing at least 29% error. If they changed it to 90 degrees, that one piece of the error goes away. That's an active document, still on the website, still trying to sell that product as a good way to measure torque. So what's wrong here? This is another process. We see this a lot. ASTM, the standard that's being followed. The verified range of forces shall not include forces outside the range of calibration. So 0 is not a force point, right? It's not in the range of calibration. If you look in the ASTM standard, there's specific guidance that says the first force point shall not be less than 400 or 2,000 times the resolution. It also says 0 is not acceptable. So right here, the first force point is 500 pounds of force. What this person is reporting is 192.3, right? So they're not following the standard, blatantly not following the standard. They've been told about it. They don't care. Don't correct it. So right processes. What do you think about this? Lower margins of safety existed here. Remember the cranes blowing over, winds. You examine this. Basically what happened is it's a practice that's pretty common. They have these pins that you put in to brace everything. And upon examination, they believe the pins were removed early. That's a process. People died that didn't need to die because someone wanted to do things quicker, right? It's a way to save time during disassembly despite the safety risk. So are we going to save time and pass that risk to others? Are we going to get caught? Maybe we're complacent. Maybe we save time for 30 years until something happens. As a measure, so right calibration provider has a measurement process and certainty capable of meeting your needs and follows published standards, replicates how the instruments are being used. That's asking the right questions, uses the right adapters to ensure results are repeatable. Competent technicians with training records, follows published standards, reports measurement uncertainty correctly, and is rated highly for on time and delivery. Our mission, which is changed, and we have right there to be regarded. Our mission is to be the best independent force and torque calibration resource in the world by providing realistic solutions and continually develop new products to meet customer needs. We also like to defy averages with 100% overall customer satisfaction. We go into our core values. If you don't have them, I suggest people make them. And it's like, what do you agree on as a company? Our number one is a positive customer experience. Our number two is accountability for all actions. Number three is teamwork above self-interest. 4 is continuous improvement. 5 is honesty and integrity. And 6 is a safe work environment. That's what we have. Those are the 6 that we agreed on as a team. All of us. We said, this is what we're going to do. This is what we're going to drive our company. This is what we're going to hold everybody that walks in our door to. So please join us in educating the people who underestimate the importance of following the standards, asking the right questions, using proper machines and adapters. Using what was presented here, you can help make the world a safer place by basically not only force and torque or whatever, you can help create a safer place by helping companies improve their measurements, right? And if you want our Excel sheet, there's a QR code you can scan. You can also go to that link. All right, thanks everyone.